And thanks for joining us on Space Nuts, where we talk astronomy and space science. So glad you could join us again this week. Coming up on episode 295, new research has suggested that coronal loops, the plasma loops that you see blasting off the surface of the sun, aren't real. They don't exist. That is fascinating. We'll look into that. And large organic molecules have been found in planet-forming disks, or a planet-forming disk. And we're going to answer a few audience questions today about the sun's orbit, about Uranus, and we've got a really fabulous question which I have not previewed with Fred because I want to surprise him. Basically, the question is black hole related, but I think it's something we haven't actually touched on much before. So we'll get into that very, very soon here on Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
My name is Andrew Dunkley. I am your host, and joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Nice to meet you, Mr. Host.
Thank you. Have you managed to stay dry in Sydney?
Oh, no. We've had the most extraordinary weather. It's been raining for days and days, but yesterday was a humdinger. It just absolutely poured down all day. We recorded 117 millimetres from 8:30 to 4:30 in the afternoon, 8:30 in the morning. And so we've got a kind of granny flat downstairs, which sits under, we've got a sort of terrace in front of the house, and the granny flat sits underneath that because the whole place is built on a hillside, succession of rock ledges, and the water came down the rock ledge underneath the terrace and flooded the granny flat. But fortunately, not to any great depth, because the granny flat has a bathroom with a drain in the floor. So there was this nice river going through the granny flat. It's a place that, as you know, Andrew, we only moved here 6 months ago, and we always knew we were going to have to renovate the granny flat. So there's no granny in it. Unfortunately, it's got a slate floor, so there's no carpets or anything. So it's
that was lucky.
Yeah. So it's painful, and there'll be a lot of work to do. But I don't think it's destroyed the fabric of the house or anything like that. But look, there are other people who are far worse.
Yeah. I was going to say, I think you've got away with it much better than many.
Yes,
I mean, the number of homeless people as a consequence of the floods in Queensland, the Northern Rivers, down around parts of Sydney, it's just been dreadful. They were saying it's the wettest start to a year ever recorded in Sydney since records began in the late 1800s. And the biggest flood they've ever had in Lismore since records began. And looking at my hometown where the Hunter River flows, it's right up to the edge of the South Bank.
Yes.
And it has not been in the CBD since 1955. So let's hope that stays out. The good news is that East Coast low has moved offshore. So fingers crossed that that's the end of it. But it won't take much more rain to tip over a few more rivers. It's been dreadful.
That's Maitland, is it?
Maitland's my hometown.
Yes, that's right, I thought.
And hello to everyone in Maitland that listens, mum and dad, basically. All right.
I'm amazed they do too.
Thank you for that.
Yeah.
All right, let's get down to business. And new research has suggested that coronal loops blasting off the surface of the sun are an optical illusion. This is a fascinating story. And we're so close to the sun, you'd think, we've got it all figured out. We know everything. But we're talking about those plasma bursts that sort of blast off the surface and then they loop back down and they make these beautiful arcs. But apparently they, according to this research, and it's not absolute, but they've been doing some modelling, not real. How so?
I think the research is that not all of them are real. I think there's a lot of uncertainty here, but it does emphasise, Andrew, just how much we rely on the way things look in astronomy, and then try and figure out what's really happening. And I don't know. When I look at a coronal loop, I think that the normal explanation works really well, and that is that. There's actually probably we could point people to the SciTech Daily website, where there's a lovely picture from one of NASA's spacecraft of a coronal loop, or a set of coronal loops. And what they do is they kind of join sunspot pairs. Our traditional view of sunspots, which we've had since pretty well the invention of the telescope, is little dark patches on the surface of the sun. That's how they show up in a normal telescope. But we now know that they're regions where there's intense magnetic activity, and so it's been realized that what probably causes sunspots is the darkening comes about because of a reduction in temperature of the surface of the sun. So, it's contrasting. I think it goes down by 1,000 degrees or something. And when you contrast that with the 5,000 degrees of the sun's surface, it looks dark. But as I said, all we see is the dark spots, and we think the reason why they're darker and cooler is because the radiation coming up from within the sun is blocked by intense magnetic activity within these sunspots. Now, today we have the benefit of telescopes on spacecraft which are in orbit around the sun, and so we can look at sunspots from the side. We can see them on the sun's limb, and what we see are these loops of plasma joining sunspot pairs. The sunspot pairs have opposite polarity, north and south magnetism, and so it's just like a bar magnet. Almost looks like a bar magnet with a loop of, rather than iron filings, as the old school science experiment shows. What you've got is these plasma loops joining the poles of the magnet, and that actually is a perfectly reasonable explanation. And certainly, for when you look at these things, it's intuitively what you expect that to be. But this is new research that's come from scientists at the National Center for Atmospheric Research in the United States, which is based on 3D simulations of what's happening within the solar corona, the outer atmosphere of the sun. So the simulation actually was worked on a few years ago, but what has happened is so you've got this kind of 3D model of the sun's atmosphere, and what you can do is look at it in different slices, if I can put it that way. It's a bit like tomography, medical tomography, where you've got lots of different slices through somebody's body, the brain, for example, or people's organs. But you're doing the same thing, but it's with the sun's atmosphere. And what they've found is that some of these loops may not be loops, but what are described as wrinkles of bright plasma in the solar atmosphere. Okay. And it's apparently, if you imagine sheets of brightness which are kind of folded over themselves, so then you get something that looks like a thin bright line as these plasma sheets, and it looks exactly like what the coronal loops look like. They actually, this research team have got a name for it. They call it the coronal veil hypothesis, but it actually has big implications. If most of these loops that we see are not actually loops but are wrinkles in the plasma sheets, then what it does is it changes our understanding of the way the sun works, because coronal loops have been, they've been built into our understanding of the theory of the processes going on in the sun, and the way we make measurements of things like the temperature of the sun's atmosphere, its density, and things of that sort. There is a quote from one of the scientists who was involved with this study. In fact, this is the person who led it. Let me see if I can pronounce her name. Anna Malanuchenko. She says, "I have spent my entire career studying coronal loops. I was excited that this simulation would give me the opportunity to study them in more detail. I never expected this. when I saw the results, my mind exploded. This is an entirely new paradigm of understanding the sun's atmosphere. And so, I think what these researchers are saying, Andrew, is that not all coronal loops are these coronal veils, as they call them, but a lot of them are. And I think one of the things they point out is that we've been deceived in a way, that these coronal loops look so much like what I just mentioned, the way iron filings orientate themselves along magnetic fields, that they're just thought to be, that they were naturally assumed to be the same sort of thing, but with a plasma rather than with iron filings. However, there's been, there have been areas in the study of these things that people have not understood, because they would. One of the things that has been picked up is that if you think of the iron filings on a sheet of paper with a magnet underneath it, and the iron filings are tracing out the field lines, when you get away from the poles, the field lines spread out. They get closer together when you get near the poles of the magnet, and the coronal loops don't do that. And you've only to look at a few pictures of them to show that the loops themselves, they kind of stay parallel to each other. They don't spread out in the same way as the iron filings do with the bar magnet.
Could that be some kind of gravitational effect, though? Well,
you're right that the conditions in the atmosphere of the sun are vastly different from on a bit of paper with iron filings on it. Yeah. But I think there is a lot of interest in the idea that these plasma wrinkles might solve some of these issues that have been found because of the coronal loops, if I can put it that way.
One interesting thing about this announcement is that they're the first ones to say, look, this is not an absolute. This is just based on modelling. There's a lot more that has to be done before we can say for sure that what we've discovered is this wrinkle effect. But they seem pretty confident.
Yeah, that's right. There's some other really nice quotes from Dr. Malinushenko. This study reminds us as scientists that we must always question our assumptions, and that sometimes our intuition can work against us. And another one talking about what the next steps are to try and investigate how many coronal loops are actually optical illusions. In other words, these wrinkles. She says, we know that designing such techniques will be extremely challenging, but this study demonstrates that the way we currently interpret the observations of the sun may not be adequate for us to truly understand the physics of our star. Beautifully put.
Yes, indeed. Definitely. Yeah. I find magnetism fascinating.
Yeah.
Is it something that we're still learning about and trying to understand?
Yes, although I have to say our understanding of it is a lot more complete than it was when I was a lad. With the fact that we know that magnetism is carried by the photon, the subatomic particle that carries electromagnetism, and once you've got a quantum theory of a force like magnetism, you've gone a long way to solving some of the problems. But I suppose what is less well known is how magnetism behaves in extreme environments, which it go from the atmosphere of the sun to the region around a black hole, where we think magnetism actually dominates some of the phenomena that we see in connection with black holes. The idea that jets of material are squirting out from their northern and southern poles, they come about because of extreme magnetism. And I suspect our understanding of those extreme magnetic fields are still not as complete as we'd like them to be.
We'll get there one day, I'm sure.
I hope so, yeah. I hope so. I hope you and I are still around to talk about it, Andrew.
Yeah, well, you never know with astronomy.
You never know, that's right.
Once in a while, they just throw up an answer to a question and you go, oh, it wasn't so difficult.
There was, yes. Yeah, that's right.
Once in a while.
Once in a while, indeed.
All right. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Before we get to our next topic, a reminder that we are on social media. If you're a social media user, you can go to the official Space Nuts Facebook page because we put a lot of information there, lots of astronomy stories, and a really big following as well. But if you want to talk to each other, you can do that through the Space Nuts podcast group on Facebook. There are well over 3,000 followers there now, and I know everybody, well, not everybody, but a lot of people talk to each other on a regular basis, and it's a really good place to get together and talk astronomy and space science. So check it out, Space Nuts Podcast Group on Facebook, and join and get together with like-minded people and post your questions, post your pictures. Lots of people post their astrophotography, which is fantastic. Gee, there's some talented people out there working in their backyards or off the back of their utes or wherever. We're also on Instagram and Twitter and a couple of others that I can't remember. But social media is certainly a place where lots of people can get together and talk astronomy. Now, Fred, let's get to our next story. This one, too, seems to have been a never-before-seen discovery, that of large organic molecules that have been found in a planet-forming disk. They've never seen that before.
No, that's right. And this is a story that comes from our favourite millimetre wave telescope, Andrew, in fact, put it that way, from ALMA, the Atacama Large Millimetre Submillimetre Array down there in Chile, which looks at some of the highest frequencies that radio astronomers have access to, and it's it's at 5 kilometres high to get it above the water vapour, most of the water vapour in the Earth's atmosphere, which submillimetre telescopes don't like because water spoils the view. So what have we got? We've got a story about a star which we know has a planet-forming disk around it. The star has the rather brief name of IRS-48. It's not one of those long gobbledygook names that we usually talk about, but the
very, very taxing to work with, that one.
Yeah, that's right. It's actually a star in southern hemisphere, as you'd expect, because ALMA's looking in the southern hemisphere in Ophiuchus at a distance of 444 light years, and the telescope has actually studied this star quite a lot, and other telescopes have too, because the disk has got this. I don't know what to call it. It's described in the European Southern Observatory's press release as a cashew-shaped dust trap in the protoplanetary disk. So if you imagine this disk of material, there's one bit of it that's shaped like a cashew nut that's brighter than the rest. I always struggle with that word, Andrew, because my mum always used to call them cashew nuts, and when I say that, everybody laughs at me.
Did you know you can't eat them raw?
Yes, they're poisonous or something, aren't they? They're horrible, yeah.
Yeah, you've got to roast them.
Yeah. Anyway, that's an aside. This dust trap is shaped like probably a roasted cashew nut, and it's there because it seems to have a collection of bigger dust particles in it than there are in the rest of the protoplanetary disk. And so the suggestion is that somewhere in this region where this so-called dust trap is perhaps a newly born planet, or maybe even a so far invisible companion star. But this cashew nut shaped cloud of stuff going around the star has these essentially large dust grains, millimeter size, they're saying, which is huge compared with what you normally find in the protoplanetary disk of a star, which are typically, thousandth of a millimeter across. These things are 1,000 times bigger than that. Sorry, Andrew, go on.
No, carry on. I was just, I was surprised by the size when you mentioned it.
Yeah. So these are, you expect to see this because that's how planets are made, by dust grains sticking together and eventually growing into bigger things. Then they become comets or asteroids. Protoplanets, planetesimals are the first stage in planet growth, and then protoplanets, and then planets. So this is clearly a planet factory. But what has struck the scientists and resulted in this paper is that there is, for the first time, a particular molecule has been found, which is a particularly large one. And that molecule is dimethyl ether, which tells you it's carbon containing, an organic molecule. And it is seen in the clouds where stars are being formed, those nebulae, which are, the what you might call the birthplaces of stars. It's been detected there, but it's never been detected in the disk. And what that suggests is that in the sort of cold temperatures of the planet forming disk away from the star, you've got this stuff, dimethyl ether, making a sort of ice that coats the dust grains. And so what happens is that the particles of dust that are sort of nearer to the star, they essentially release that ice as a gas. That process is what we call sublimation, where it goes straight from an ice to a gas. And then those molecules are detectable because that's how ALMA sees them when they're in their gas form. There's a few nice quotes from the lead author, who's actually a master's student, believe it or not, at Leiden Observatory in the Netherlands, Nashanti Brunken, I think is his name, or her name, I'm sorry. I don't know which way that refers. I might find out in a minute.
I'm not bailing you out on that one either.
No, I know. Nashanti says, from these results, we can learn more about the origin of life on our planet and therefore get a better idea of the potential for life in other planetary systems. It's very exciting to see how these findings fit into the bigger picture. Fabulous quote, actually, and pretty wise stuff coming from a master's student. There was another quote actually from Nashanti which I liked, except it's gone. I think this one comes from Njenka van der Marel, another researcher at Leiden, who says, we are incredibly pleased that we can now start to follow the entire journey of these complex molecules from the clouds that form stars to planet-forming disks and to comets. Hopefully, with more observations, we can get a step closer to understanding the origin of prebiotic molecules in our own solar system. So some very nice quotes there from the authors of this paper, showing how a discovery like this fits into the big picture, because these are building blocks of life. They're still not living organisms, and they're not even what you might call prebiotic molecules like amino acids and sugars, but they're the stepping stones towards those molecules being formed, and they're there in the just the disk of stuff from which planets are made. So the suggestion is always going to be that these molecules, the ones that we have around us here on Earth, possibly predate the solar system. The molecules that make up our cells might contain elements that were there before the solar system was formed.
Is it fair to ask a question as to why it would be found in a planet-forming disk when we've never seen it before?
Yeah, I think the probably the thinking is that, yes, you find them in the clouds in which stars are born, but those clouds generally are very, very cold. And once you start churning up stuff gravitationally so that you've got a star that is formed by the collapse of gas raising the temperature and causing nuclear fusion to start, you might expect the radiation from that process to destroy the molecules, essentially. But the molecules have survived, and they're in the disk around the planet. So that's why it's an exciting step that the molecules are not destroyed, by the process of the star switching on. Which, I think it's really interesting stuff that, I guess 20 years ago would have thought all of these molecules that make up our bodies and our cells were formed on Earth, that they were all formed in the relatively cool temperatures that we experience here on Earth. But here's evidence that no, they actually exist in the sort of birthing ground of planets, the protoplanetary disk. It's remarkable, I think, a great discovery.
Yeah, fantastic. And I've just done a bit of social media stalking. Nashanti is from the Caribbean and is female. Okay. And I found her on Instagram. So while we were talking,
very nice, very nice. So thank you for rescuing me from that, Andrew. And
apologies, I wouldn't.
Apologies, yeah, you couldn't help yourself. Apologies for getting it wrong the first time around. It's terrible that you.
That's all right.
Yeah. Anyway,
it can be difficult sometimes with people's names. I mean, you really don't know when you see the name Fred whether it's a female or male.
Well, my younger son used to have a landlady called Fred, so that's right.
There you go.
Yeah.
Well, when we chose our eldest son's name, it was a predominantly male name, but these days it's a unisex name, Kyle, Kyle.
Yes, that's right. Yeah.
Although he's started his own Facebook thing about the number of people that write to him and call him Kylie. It happens a lot.
Okay.
So yes. Anyway, that's by the by. This is Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, thanks to our patrons, the people who put their money where our mouths are. I think that's the way it works. And if you would like to become a patron, jump on our website and click on the supporter button and find out how you can support us. And you can do that through Patreon. You can do it through one-off donations through PayPal, or you can just buy us a cup of coffee, which someone actually did literally, the Parisian Panda. Thank you. And Fred's got a cup of coffee as I speak. But yes, we do appreciate your support, and we've got a lot of supporters through the various platforms, and we thank you for that. Now, Fred, time to try and answer some questions. And our first question today comes from Andrew in Victoria.
Hi, Fred and Andrew. It's Andrew Dixon from Glenroy in Victoria. My question is, does the Sun have a predictable orbit around the galactic centre? And if so, does this have any effect on Earth, such as climate or habitability? Thanks, guys.
Thank you, Andrew. Lovely to hear from you as I knock everything off my desk. Yes, does it have a predictable orbit, etc.?
It does. Well, it's got an orbit, certainly around the galactic centre. It takes roughly 200 million years, a bit more than that, I think, is the current estimate, to go around once. 200 million years is, it's a thoroughly geological timescale. And so what makes it perhaps not predictable is the fact that the Sun is just one of maybe 200 billion stars in the galaxy, and other massive objects like giant molecular clouds, things of this sort, which are places where stars are formed. And all of these things are going around the galactic center. So unlike the solar system, where you've got just a few planets whose gravitational influence can be accurately calculated, so you can work out the Earth's orbit to a very, very high degree of precision, the Sun's orbit around the galactic center is not like that, because there's so many conflicting gravitational pulls that the details of the orbit would be quite complex. So yes, whilst it is in probably a fairly circular orbit around the center of the galaxy, because it's part of the disk, and disk objects are largely circular in their orbits, that means, in that regard, we know that it's roughly circular, but there would be details of the exact mechanisms of the orbit that would be influenced by other stars, by giant molecular clouds and the like. And just one thing to contrast it, we know that stars in the galaxy's halo, and other objects like globular clusters, which are predominantly in the galaxy's halo, they move in really quite elliptical orbits. They're elongated orbits, unlike the objects in the disk, which are much more circular in their orbital motion. Has our climate and other aspects of the Earth been influenced by this? Probably, in the sense that we may have had times when the interaction between the sun and another passing star might have perturbed the orbits of planets and things of that sort. We don't know the details of that, but that's one of the possibilities. It's also possible, and this is a theory that actually goes back to two guys I worked with at the Royal Observatory in Edinburgh in the 1970s, Victor Klube and Bill Napier, that as the sun in its orbit around the galactic centre goes past things like giant molecular clouds and other stars, the gravitational influence of those external objects can disturb the Oort cloud, the sort of spherical reservoir of comets that we have around the sun, and start tipping comets into the inner solar system. And scientists have looked for sort of periods in the cratering record of planets which might speak of episodic bombardment, where you get an episode of bombardment because we've gone past something that's disturbed the Oort cloud and sent all these comets in our direction. And that's still certainly a distinct possibility that kind of event has affected the Earth, that we might have gone through, in the Earth's 4.57 billion year history, we might have gone through periods where there's been bombardment caused by the sun's interaction with other objects near its orbit around the galactic centre.
Wow.
Long answer to a short question, but yeah, it's an interesting one.
Yeah. Great question, though. Thank you, Andrew. Lovely to hear from you. Let's now go to, a semi-regular. Haven't heard from him in a while. It's Rusty in Donnybrook.
Hey, guys. It's Rusty in Donnybrook. The moon occults Uranus tonight, and I'm just wondering what we can learn from this that we don't already know about Uranus. I understand these events are fairly rare. So, very interesting.
Okay. So what's he actually suggesting? Sorry, I've got one playing that shouldn't. I'll get back to that in a minute.
All right.
Yes.
Yep.
Trials and tribulations of a live scenario that I wasn't planning.
Okay.
Yeah. So Uranus occult.
The moon occults Uranus, yeah.
Yes. So what's the story?
So these things were scientifically important in the era, first of all, when we were trying to refine orbits to ensure that the orbit of Uranus was well understood. And of course, that's got a history going back to almost to the discovery of Uranus, because it was through wobbles in Uranus's orbit that we found that there was a planet called Neptune. Didn't know it was called Neptune, but it was the gravitational influence of Neptune on Uranus's orbit that led to its discovery. And more circumstantially, because there's no real connection, it led to the discovery of Pluto as well, even though Pluto is far too small to have any influence on Uranus's orbit. So in those days, when you're trying to pick out, to determine accurately the orbits of things, you will be interested in an occultation, because you've got this instant when you know that the limb of the moon and a planet are in exactly the same direction. And so it pinpoints them. There was a time as well, excuse me, again, this goes back to my earliest days in astronomy, because I was involved with this, where we used to use occultations of stars by the moon to work out what the geography of the moon was like, especially near its poles, because you could see stars that would, if the moon was sort of just kissing the star as it went past, the star would appear and disappear and appear and disappear as you saw it through gaps in the mountains near the moon's poles. Excuse me. And that was quite important too. But today, I think it's more of it's a bit like an eclipse of the moon. It's a phenomenon that we understand well, and there are things that you can learn from an eclipse of the moon. In fact, you can probably learn more from an eclipse of the moon than you can from an occultation of Uranus. What's more interesting, sorry to labour the point, Andrew, is if Uranus passes in front of a distant star. So that's an occultation by Uranus of a distant star, because then the star will fade as it goes behind, as its light starts filtering through Uranus's atmosphere. And you can actually observe that light and look at some of the chemical elements in the atmosphere of Uranus by noting what spectral signature is placed on the light by the starlight having passed through the atmosphere of Uranus. So that sort of thing's much more useful. In fact, it's how we discovered Pluto had an atmosphere, by observing an occultation of a star by Pluto. This happened at least a decade ago. Certainly one of those observations we were involved with at the Anglo-Australian Telescope. So, yeah, go ahead.
Given how many stars there are that we can observe, are occultations like that common?
Yeah, relatively, although, you know, I mean, it depends how bright you can go or how faint you can go when you're looking at the stars. The fainter you go, the more stars you can see being occulted. But then you've got the problem that in the case of a planet, the planet is much, much brighter than the star that's being occulted, and so the observations get difficult. Yeah,
fair enough. Yeah. All right, there you go, Rusty. No, but yes.
The answer, no.
All right, we'll go to our final question, and I've been saving this one up. This is going to be a bit of a surprise for Fred, because usually we preview the questions together, but I wouldn't let him listen to this one. This is Amelia.
Hi, Fred and Andrew. My name is Amelia from Pennsylvania in the United States. I know when some stars die, they turn into black holes. But what happens when black holes die? I got Fred's book, Space Warped, for Christmas. I've read up to page 21 so far, and I really like it. Thank you.
Oh, whoa. So lovely.
Yeah, that's delightful.
Yeah. Thanks, Amelia. Great question. And yeah, I'm so glad you're enjoying Fred's book. It's so nice.
That's fantastic.
She'd be the first one.
It's certainly the first one I've heard from. Yeah.
Oh, that's lovely.
So thank you.
So good to hear from younger listeners too.
Yeah.
We've got a few, but yeah, terrific. So what happens when a black hole dies, Fred?
Yeah, it's a really good question as well, and we don't really know. We know that if two black holes collide, they just make a bigger black hole. So you know, they don't wipe each other out or anything like that. You just end up with a bigger black hole. And we also know, and this is probably the real answer to the question, and this is work that was done by Stephen Hawking the late great Stephen Hawking back in the 1970s. We know that black holes evaporate; they don't last forever, and we always assume that nothing can escape from a black hole. But there is this process called Hawking radiation, which is a kind of leakage of energy, and it is radiation, it's electromagnetic energy, so it's light and heat, that leaks out very, very slowly from black holes, and eventually a black hole would disappear altogether. It's called black hole evaporation, but the timescales for that are huge. They're much, much longer than the age of the universe. These things, you know, we believe that these things take a very, very long time to evaporate. So perhaps they do just fade away. They you know, just disappear. They dry up in a sense, but it's a long process, and we might have a long time to wait before we see it happening.
Yeah. Oh, yeah. I imagine we do have a long time to wait. So what would be left when it was gone? Just space?
Well, you know, people have proposed a theory that when a black hole finally evaporates, what you get left behind is a white hole.
Yes, I've heard that one.
Yeah, which is the opposite. You know, it's something that nothing can go into, but stuff can come out of. So as the universe ages and we get more and more evaporating black holes, maybe we'll start to see white holes. We've never seen one.
No, they're just theorized.
They're just theorized, that's right, yeah.
We have had questions about them in the past, but never been seen. So at this point, they don't exist.
They are not known to exist. That's the way to put it.
Always quick to qualify.
Well, in astronomy, you can't, we would have been talking with absolute certainty about coronal loops until this week.
Indeed. That's very true. Thanks, Amelia. Thanks for your question, and lovely. Thanks for the book endorsement. And I will remind people that if you do have questions and you want to buy Fred's book, you can go to our website, spacenutspodcast.com or spacenuts.io, and click on the shop link, and you'll find Fred's book in there and all our other bits and pieces. You can buy shirts. Look, I've got the black one on today.
Oh, yeah. Well, that's rather nice. Yeah.
Yeah, it's nice, this one. I like this. And everything else that we've managed to put our logo on is on the Space Nuts shop. And you can ask your questions through the AMA tab or the Send Us Your Voice Message link on the right-hand side. It's pretty easy stuff. spacenutspodcast.com or spacenuts.io. Now, little announcement, preempting episode 300. We've been taking in your ideas. We're considering guests. But we are looking at doing a live show. We think we've figured out a way of doing it. We're going to do some tests, but the plan is to go live. So we'll let you know when. We will have a special URL that you can log into, and if all goes well, it will automatically link you to us live via your preferred podcast distributor. So leave that one with us. But we're hoping to do a live show for episode 300, which should fall sometime around the second week in April, the way my numbers stack up. I thought it was going to fall on my birthday, but it's not. It's going to be a couple of weeks later than that. But yes, that's where we're at the moment with episode 300. Because it could all fall over and we'll just do a normal one. But we'll see what happens. Fred, it's been a pleasure as always. Thank you.
Great pleasure, Andrew, as always too. And looking forward to next week and to getting to episode 300. That's a bit of a milestone, isn't it?
Sure is. Yeah, many milestones. I think by the time we get there will be a white hole discovered.
Maybe so. Wouldn't it be good if we had a big discovery like that to celebrate in episode 300? Yeah,
would be nice. All right, Fred. Thanks very much. I'll see you next week.
Take care, Andrew.
You too. Bye-bye. Stay dry. Fred Watson, astronomer at large, part of the team here at Space Nuts, and another one that's ringing out his toupee at the moment is Hugh. Thanks to Hugh in the studio for pushing all the right buttons, which I didn't do very much of today. But from me, Andrew Dunkley, thanks for your company. Look forward to catching up with you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.